Even as DeepSeek has been busy recruiting heavily, it has never lost sight of open source. Today, DeepSeek and a team from Peking University jointly released a paper titled DSpark, Confidence-Scheduled Speculative Decoding with Semi-Autoregressive Generation, introducing a new large model inference acceleration framework called DSpark. The paper reveals that DSpark has already been deployed in the production serving systems of DeepSeek-V4-Flash Preview and DeepSeek-V4-Pro Preview, replacing the previous MTP-1 approach. Under real online user traffic, with total system throughput held constant, DSpark increased per-user generation speed for DeepSeek-V4-Flash by 60% to 85%, and for DeepSeek-V4-Pro by 57% to 78%. With speed gains like this, what secret sauce did DeepSeek feed its inference engine? Admittedly, some of what follows can feel a bit dry, but if you are interested, I invite you to read on with patience. The world has long suffered from AI that types one word at a time. Why does waiting for a large model's reply so often feel like squeezing toothpaste out of a tube? The reason is not complicated. Mainstream language models generate text using an autoregressive approach. Every time the model produces a new token, it must perform a forward pass conditioned on all preceding context to SO. The longer the output, the more decoding steps are required, and latency accumulates easily. In highly interactive settings like real-time chat, multi-turn agent workflows, or coding assistance, generation speed directly affects user experience and GPU utilization. Speculative decoding was invented to address exactly this. The idea is akin to having a small model write a draft, then having a large model quickly review it. The system first uses a lightweight draft model to generate a batch of candidate tokens, and then the target model, the one actually responsible for output quality, verifies these candidates in a single pass. Tokens that pass verification are accepted. The moment a token is rejected, all subsequent candidates are discarded, and the target model generates one corrected token. Because the verification stage can be parallelized, speculative decoding can improve generation speed without altering the target model's output distribution. More intuitively, the goal is to let the large model confirm multiple tokens in one forward pass, instead of only one at a time. Speculative decoding has already become an important direction for accelerating large model inference, but existing approaches still have clear limitations. The first category is the autoregressive draft model. Like a normal language model, it generates candidate content token by token. The advantage is more natural sequential relationships and higher candidate quality. The obvious downside is that when the draft model writes its draft, it must also proceed step by step. The more candidate tokens it produces, the slower the draft stage becomes. The second category is the parallel draft model. It can generate multiple candidate tokens at once, which is very fast and better suited for producing longer candidate blocks. The problem is that the tokens inside a candidate block lack sufficient dependency on each other. The paper gives a highly intuitive example. Faced with a certain context, a model might have two reasonable continuations, such as of course and no problem. Because a parallel draft model does not truly generate in order, it can easily mix up the two continuation paths and produce an inconsistent combination like of problem or no course. The result is that while the first few tokens from a parallel draft model are often decent, the probability of later candidates being accepted by the target model drops off fast. The paper calls this phenomenon suffix decay. A more practical problem arises in online serving. A parallel draft model can easily generate a long string of candidate tokens at once, but in a real high-concurrency service, sending all of them to the target model for verification may not be worth it. On structured tasks, like math and coding, the answer path is relatively narrow, so candidate tokens are more likely to be accepted. In open-ended chat, uncertainty is much higher, and later tokens are more likely to be rejected. When the system is idle, verifying a few extra tokens doesn't matter much. When the system is busy, verifying tokens that will most likely be rejected eats into batch capacity and affects other user requests. In other words, the problem with speculative decoding is no longer just about whether you can generate more tokens in one go, but also about which tokens are worth sending to the target model for verification. How DSpark achieves both at once. Spark's philosophy can be summed up in two parts. Make the draft more coherent, and make the review better at prioritizing. On the generation side, DSpark adopts a semi-autoregressive architecture. It preserves the backbone of a parallel draft model so that the bulk of the computation still happens in one shot. At the same time, it adds a lightweight sequential module at the output end, allowing later tokens to reference the tokens that have already been sampled before them. You can think of it this way. First, spread out candidates quickly using a parallel method. Then use a very light sequential module to check the coherence between adjacent tokens. The paper uses a Markov head by default, and also tested an RNN head. The Markov head mainly models the transition relationships between neighboring tokens. It is computationally cheap and easier to deploy. The RNN head can retain longer history within the block, but the benefit is limited and the complexity is higher. Therefore, the paper keeps the Markov head as the default. The goal of this architecture is clear. Retain the speed of a parallel draft model, while partly restoring the forward coherence of an autoregressive draft model. On the verification side, DSpark introduces confidence-scheduled verification. The system predicts a confidence score for each candidate position. This score indicates, given that all preceding tokens have already been accepted by the target model, how likely is the current position to also be accepted subsequently. A hardware-aware prefix scheduler dynamically decides how many tokens to verify for each request, based on three factors: current system load, the confidence score at each candidate, position, and the engine's throughput curve across different batch sizes. Therefore, DSpark does not mechanically verify a fixed-length candidate block. When system resources are abundant, it can verify a longer prefix, allowing one target model forward pass to yield as many effective tokens as possible. When system load increases, it shortens the verification length for low-confidence requests, reducing their footprint on the target model's batch capacity. This is also where DSpark comes closer to real production environments than traditional speculative decoding. It pursues not only generating more candidate tokens in one shot, but also adjusting the verification budget according to system load. The endgame for large models is a complex systems engineering problem that in the offline experiments. The paper tests DSpark on 4 target models: Qwen 3-4b, Qwen 3-8b, Qwen 3-14b, and Gemma 4-12b, and compares it with 2 representative baselines: the autoregressive draft model Eagle 3 and the parallel draft model D-Flash. The evaluation covers 3 scenarios: math reasoning, code generation, and everyday chat, and includes benchmarks such as GSM-8K, Math 500, M25, MBPP, Human Eval, LiveCodeBench, MTBench, Alpaca, and ArenaHard. The results show that on Qwen 3-4b, Qwen 3-8b, and Qwen 3-14b, DSpark improves macro average accepted length over Eagle 3 by 30.9%, 26.7%, and 30%, respectively. Compared with DFlash, the gains are 16.3%, 18.4%, and 18.3% that on Gemma 4-12b. DSpark also maintains the lead. Accepted length can be understood as the average number of tokens accepted by the target model in each round of speculative decoding. That a higher number means the draft model's output is more likely to be approved by the large model, which also expands the room for inference acceleration. The paper also observes substantial variation across different tasks. Taking Qwen 3-4b as an example, Spark's average accepted length is 5.57 on math tasks, 5.12 on code tasks, and 3.49 on chat tasks. Math and code are more structured, with more stable continuation paths. Chat is more open-ended, and a model can have many plausible ways to respond. Thus, candidate tokens of the same length do not hold the same value across different tasks. That a fixed verification length would waste some computational resources. More detailed experiments explain why DSpark works. That a parallel draft model like DFlash is very strong on the first candidate token because it can use a deeper network to generate candidates all at once. But from the second token onward, it lacks intra-block dependency, and its acceptance rate drops more noticeably. An autoregressive draft model like Eagle 3 has better coherence later in the sequence, precisely because it generates in order. However, to keep draft stage latency under control, it usually cannot be made too deep, so its predictive power on the first token is limited. That DSpark sits between the two, that the first token inherits the strong prediction capability of a parallel draft model, and the subsequent tokens reduce suffix decay through the sequential module. Structural experiments support this picture. The paper shows that a 2-layer DSpark already surpasses a 5-layer DFlash, indicating that lightweight sequential modeling is more effective than simply adding more parallel layers. As the proposal length increases from 4 to 16, Spark's advantage over DFlash continues to widen. Under the longest setting, DSpark leads DFlash by 30%, 26%, and 22% on math, code, and chat tasks respectively. In terms of latency, the extra overhead introduced by the sequential module is very small. In a test with batch size 128, compared with DFlash, DSpark increases single-round latency by only 0.2% to 1.3%, while accepted length improves by up to 30%. The confidence module was also validated in isolation. The paper performed a confidence threshold sweep on Qwen 3-4b, progressively raising the confidence threshold and observing which tokens the system retains. The result speaks for itself. The higher the threshold, the more low-value candidate tokens the system filters out, and the higher the overall acceptance rate. The effect is most pronounced on chat tasks, where the acceptance rate climbs from 45.7% to 95.7%. On math tasks, from 76.9% to 92.5%, and on code tasks, from 67.6% to 92.0%. The online deployment section is even more critical. DeepSeek deployed DSpark in the production engines of DeepSeek, V4-Flash Preview, and DeepSeek, V4-Pro Preview, with the maximum draft length set to 5, and compared it against the previous MTP-1 production baseline. MTP-1 only performs single token prediction, so its room for acceleration is limited, but it is relatively safe under high concurrency. The reason is that a static multi-token draft, while seemingly generating more tokens at once, can actually waste the target model's verification resources if many tokens end up being rejected, thereby dragging down total system throughput. Spark's significance lies in making multi-token drafts controllable under real online traffic. Under moderate concurrency, DSpark expands the verification budget from MTP-1 static 2 tokens to roughly 4 to 6 tokens, allowing each forward pass to produce more effective output. When concurrency rises further and the target model approaches saturation, DSpark automatically shortens the verification length, reducing the batch capacity consumed by low-confidence tokens. In online testing, with V4-Flash running at a service target of 80 tokens per second per user, DSpark increased total system throughput by 51% over MTP. Under the stricter target of 120 tokens per second per user, MTP-1 was already near its serviceable limit, and DSpark delivered a nominal throughput advantage of 661%. This 661% should not be interpreted as a more than six-fold improvement in all ordinary scenarios. A more accurate understanding is that under high interaction workloads with tight SLA constraints, MTP-1 already struggled to sustain service capability, while DSpark opened up a performance region that was previously hard to reach. The trend for V4-Pro is similar to 35 tokens per second per user. DSpark improved total throughput by 52%. At the stringent target of 50 tokens per second per user, the nominal throughput advantage reached 406%. Under the same system capacity, DSpark increased per user generation speed for V4-Pro by 57% to 78%. At the end of the story, it is naturally the familiar recipe and the familiar flavor. DeepSeek also announced that it is open-sourcing the DSpark model weights, including the DSpark checkpoints corresponding to DeepSeek, V4-Flash Preview, and DeepSeek, V4-Pro Previewed at the same time. DeepSeek open-sourced DeepSpec, a codebase for speculative decoding training that includes Eagle 3, DFlash, and DSpark. In short, accelerating large model inference is no longer just a model architecture problem. It is increasingly a systems scheduling problem. Simply letting a draft model generate more tokens in one go does not necessarily mean the service will actually be faster. Candidate token quality, acceptance rate, verification length, system load, throughput targets. Every variable is pulling on every other variable in an exquisitely delicate way. Large model competition is entering a more refined phase. Training stronger models remains the hard power at the table, but whether you can deliver those models to real users faster, more cheaply, and more stably also determines the ceiling of an AI product. By choosing to open source this inference acceleration experience from its own production environment, DeepSeek is essentially sharing, selflessly, a set of core methods that can truly improve inference efficiency and lower serving costs with the entire industry. One can only say, don't be too open AI. Learn more from DeepSeek.